In question number 3, they're asking us to write an equation in standard form, that's ax squared plus bx plus c, that passes through the given points. To do that, we're going to start by taking each of the points and thinking about what they're really giving us. A point always consists of an x-coordinate and a y-coordinate. So if we label each coordinate as x and y, it might become a little more obvious here that the only way to approach this problem is by plugging in the x and the y into the corresponding spaces in the original equation that they gave us. If, for instance, I plugged in 0, -1, that would give me, instead of y equals, -1 equals a times 0 squared plus b times 0 plus c. So notice I just kept the original equation that they gave me and plugged in x and y from the point into the corresponding spaces. I'm going to do the same thing for the other points that they give me as well. So if I use 2, 23, that would give me, when I plug it in, 23 for y equals a times 2 squared plus b times 2 plus c. Again, notice I just plugged in the 23 for the y, the 2 for both of the x's. The last point they gave me was 3, 50, so I'll do the same thing. That gives me 50 equals a times 3 squared plus b times 3 plus c. Now in doing that, you can tell we've got quite a mess on our hands, so let's try to simplify these equations a little bit further, just so they look a little easier. If I start with the first equation, that's -1 equals 0 squared is 0, and 0 times a is 0. B times 0 is also 0, so the only term left over is the c. That's actually pretty convenient, because if we're trying to solve, now we actually know that the c value is -1. That's going to come in handy in a moment. If I simplify the second equation, I'd have 23 equals a times 2 squared, which is 4a, plus b times 2, which is 2b, plus c. The third equation would be 50 equals a times 3 squared is 9a, plus 3 times b is 3b, plus c. Now what we're left with is definitely a system of 3 equations. However, the first equation in the system is hardly an equation at all. It's an actual value that we can use. So one nice strategy is to plug in that value of c into both of the equations that I haven't worked with yet, because that will make those equations a little bit simpler. That'll give me, for the first equation, 23 equals 4a plus 2b, now instead of plus c, -1. And the next equation would be 50 equals 9a plus 3b instead of plus c -1. Again, to make our lives even simpler, we can go ahead and make these equations a little more graceful by combining the ones on the left-hand side to try to make those like terms go together. If I move the -1 over to the left on the first equation, I'd get 24 equals 4a plus 2b. If I move the -1 on the second equation, that would give me 51 equals 9a plus 3b. Hopefully you followed along with the process, but notice everything that we've done so far has been basic algebraic manipulation. I plugged in the x's and the y's into the equation for each point that they gave me, and then I just kind of simplified the equations. I took advantage of the fact that the first equation actually simplified a lot further than we expected, and I took the liberty of plugging in that value for c to make the original equations a little shorter and less complicated. When we look at this now system, we only have 2 variables to worry about, a and b. To try to solve them, we want to eliminate one of those variables by trying to cancel out another pair. The best pair to cancel doesn't really matter, but I'm going to select to cancel the b's. If I turn each of these into a 6, making sure one of them is negative, I can get those b's to cancel out. So I'm going to multiply the top equation times 3. I'm going to multiply the bottom equation times -2, because that would give me 6b and then -6b, which I know is going to make things cancel out. So if I multiply the first equation times 3, I'd get 3 times 24, that's 72, equals 3 times 4a, that's 12a, and 3 times 2b is positive 6b. The second equation, multiplying by -2, would give me -2 times 51, that's -102, equals -2 times 9a, that's -18a, and -2 times 3b which is negative 6b. If I go ahead and go vertically now to combine like terms, the b's will cancel out, and then I just combine like terms with what's left over. Negative 102 and 72 would be negative 30, equals 12a minus 18a would be negative 6a. And of course, if I divide to get a by itself, that means a is going to be positive 5. That, again, is extremely helpful, because if the goal of the original problem was to try to figure out the values for a, b, and c, now I'm well on my way. I know that a is 5, and I know that c, which I got originally, was negative 1. The only variable left to solve for is the b. So I can go back to either of the equations that I had created to begin with, and I can plug in the value of a that I know in order to solve for b. It doesn't matter which equation that we work with. We just try to work with whichever one looks simplest. I'm going to take the first equation just because the numbers look kind of friendly, and I'm going to plug in the value of a into its space. So I'm going to take 24 equals 4 times, instead of a, plug in 5, plus 2b. If I simplify, 4 times 5 is 20, so 24 is equal to 20 plus 2b. If I move the 20 over, that would give me 4 is equal to 2b. And then, of course, if I divide, I'll get b is 2, which means now I know all of my values. A is 5, b is 2, and c is negative 1. If I now go back to my original problem, I figured out the values for a, b, and c. So to write the equation in the proper format, I simply write the equation with those numbers plugged in. So instead of a, we'd have 5x squared. Instead of b, we'd have plus 2x. And instead of c, minus 1. So by solving the system, we essentially solved the values for a, b, and c, and plugged those values back into the standard form that they gave us at the beginning.